Bismillahirrahmanirrahim. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. My dear students, Assalamu alaikum. Today I'll start chapter 7, week 7, which is chapter about design of chilled water pipe. So just like HVAC duct design, an HVAC engineer is required to perform HVAC plumbing also. HVAC plumbing involves design of the pipe, piping layout, and of chilled water supply, chilled water return piping layout according to the drawings. It depends where chiller is located, where is the machine room, where are the room location, on architectural drawing, on site plan. The engineer should make a single line diagram of piping layout. Once that piping layout is done, depending on the cooling load of each outlet. So outlet is for water, the outlet, there is no outlet. It is actually a closed loop system. So water goes from chiller, cold water, chilled water at reduced temperature, from refrigeration machine, chiller plant, it goes to the air handling unit, AHU, or fan coil unit, FCU. So air handling unit and fan coiling units are the units. They are actually heat exchanger coils where cold water is circulated through a bunch of pipes. So that is called coil. So this, after going through the coil, it comes back to the chiller. In the coil, it takes heat from the hotter air, which comes from the cooled room. So in this way, room is being cooled. So fresh chilled water at about 6 to 7 degrees centigrade enters into the coil and leaves at 10 to 12 degrees centigrade and reaches chiller. Chiller takes this heat and refrigeration machine discharges this heat into the condenser, and condenser discharges this heat. If it is water cooled, it is discharged into the cooling tower, and if it is air cooled, it is directly discharged into the air. So engineer's requirement is to be able to design all these piping loops. One water piping loop is from chiller to the cooling tower, and other piping loop is from chiller to the cooling coils. So air cooling coils. So chilled water circulation should be continuous round the clock, and it should have least resistance to flow, and pipe sizing should be economical. So as big sizes selection means higher initial cost and more space required. So selection, it is engineer's responsibility to select material of the pipe, chilled water pipe, and its size, dimension, and fittings on the way, where it should be regulated, where the valve should be situated, and where flow meter should be inserted, and where thermometer should be inserted to know about the supply and return temperature. How the pipeline supply and return should be laid down. There are arrangements, direct return and reverse return. So you will learn about this in this lecture. So engineer does not only require to design these chilled water piping. HVAC duct is also his responsibility, and we have learned yesterday. Not only chilled water pipe, it may be hot water pipe. If it is round the year cooling system with boiler or hot water heater in the system, then hot water is circulated through the coils in winter season. So in that case, hot water loop and hot water loops are also to be designed by the HVAC engineer. There are service water connections also to supply cold water and hot water to the bathrooms and showers and things like that. So that piping design is also responsibility of HVAC engineer. If it is refrigerant flow system, any variable refrigerant flow system, VRF system, engineer is required to design that piping system also. Fuel pipe may also be required to design by the engineer in a large commercial buildings, in the large industrial and commercial buildings. So our hospitals, our universities and colleges where machine room is far away, and there are generators and there are power systems which require use of fuel. Boilers require use of fuel and there is a fuel tank outside. Fuel tank may be liquid, it may be gas. So accordingly, refrigerant piping, fuel gas piping, and fuel oil piping. There may be oil storage, and from oil storage tank to the boiler or heating furnace. So fuel supply piping should be designed. So what we are learning today is actually same theory as we have learned it in previous chapter, that is HVAC duct design. The difference is in HVAC duct, the working fluid is air. Working fluid in chilled water system is now liquid water. So formula is same, which you have learned in the subject, which is called fluid mechanics. So pressure drops when fluid is passing through a pipe. Fluid may be liquid. In this case, in our case, chilled water passes through a pipe. Then depending on the diameter of the pipe, depending on the length of the pipe, depending on the velocity of the water inside, and depending on the density of the water, that means temperature of the water. Density depends on temperature. These are the factors: density of the water, velocity of the water, diameter of the pipe, and length of the pipe. Pressure drop will take place from pump up to the supply point to the cooling coil, and back to the chilled water plant. So this whole is covered by this single formula: delta P is equal to F L by D, V square by 2 multiplied by rho, where F is the friction factor. It is a dimensionless number. It depends on regime of flow. In fluid mechanics, you've learned what is regime of flow. Regime of flow is laminar, transient, and turbulent. So depending on Reynolds number up to 2,300 it is laminar flow, and from 3,000 to 10,000 it is transient flow, and 10,000 Reynolds number, if it is higher than 10,000, then it is called turbulent flow. So rough pipe have turbulent flow. Now here delta P is the pressure drop in this formula, F is the friction factor, L is the length of the pipe in meter, and remember length can be straight portion of the pipe plus equivalent length of fittings. Just like in AC ducts, here in AC chilled water pipes also there are T's, there are elbows, there are branches. So there are reducers, there are enlargers. So accordingly, in these fittings there is a pressure drop that is called as dynamic drop, but this dynamic drop can be calculated with the help of a method which is called equivalent length. For equivalent length, we have to refer to certain handbooks where research data is available. In that data tables, you will find what is the one elbow of 50 mm diameter, how much equivalent length of pipe should be taken to calculate flow resistance through the pipe system. So this is the basic formula of fluid mechanics applicable for any fluid. It may be air, it may be gas, it may be liquid, it may be water, it may be oil, it may be fuel oil. So now, what is I had mentioned about Reynolds number, which is the criteria of regime of flow. So regime of flow may be turbulent, may be laminar. So that is why we need to know its formula. Reynolds number is equal to velocity multiplied by diameter multiplied by density divided by viscosity, mu, dynamic viscosity. Here R is the Reynolds number in this formula. Let me enlarge it for you. Oh, it's too much. So this is the formula. Reynolds number RE is equal to VD rho divided by mu, where V is the velocity meter per second of the liquid water, and D is the diameter of the pipe, inner diameter of the pipe. Rho is the density of the water. It depends on temperature of the water. Mu is the dynamic viscosity of the water, that is parts per second. It also depends on temperature. Now, in fluid mechanics, there is a very famous equation. So, what formula? This basic formula is called Darcy-Weisbach Equation in fluid mechanics books. This is classical formula, Darcy-Weisbach Equation. Now, there is another equation called Colebrook Equation for friction factor. F can be found from either Darcy's formula, from a chart called Moody diagram, which I have given to you for AC, HVAC duct design also. And now Moody diagram can be used for water also to find out this F. So if Moody diagram is not available and your calculation is software-based, computer-based, then this formula can be used in the software, and that is F is equal to 1 upon 1.142 log D upon epsilon plus D. So you can see that here we need Reynolds number to solve this equation. We need relative roughness of the pipe, epsilon upon D or D upon epsilon, and we need just the diameter, epsilon, surface roughness, and Reynolds number. Reynolds number, you know, it depends on velocity, diameter, length, and viscosity. Now, F is the friction factor in this Colebrook equation. Epsilon upon D is the relative roughness of the pipe, and epsilon is the absolute roughness of the pipe or duct, and Reynolds number is RE. Here in tables in the book, when I was in chapter 6, I was explaining how we learn AC ducts, HVAC ducts, so air duct. So air ducts, we use this data for roughness. So surface roughness is given here for different materials, repetitive steel, concrete, cast iron, etc. And here velocity standard at, sorry, in this table is given a property of fluid, in this case viscosity of dry air. But in chilled water piping we don't need this, but we need the same concept used here. We need the equivalent data calculations also on the same principle which was done for HVAC duct, and this is the formula which converts. This is simple formula 2AB divided A plus B. Actually, in calculation, we usually have design tools which are called as diagrams, charts, calculation charts and diagrams. They are on logarithmic scale, and we are given circular duct dia, circular pipe dia. So if actual dia is rectangular, we have to convert it into rectangular, or if it is rectangular from circular dia calculation, we have to convert it into rectangular size. So this is the formula: 4 multiplied by area divided by perimeter. This is also always taught in fluid mechanics books. If regime is if regime is laminar, so flow is slow and its Reynold number ranges up to 3000, then we can use very simple formula. We don't need go to Moody's diagram. We need only 64 divided by Reynolds number. Just calculate Reynolds number, and from there 64 divided by Reynolds number, you will get this factor. This factor for fluids is for surface roughness equal to 0.006 meter. This factor is usually from 0.01 to 0.1. So this depends on flow regime, and this depends on surface roughness. Here is Moody's diagram. You can see this is Moody diagram, and in this Moody diagram, here is friction factor F. It ranges from 0.008 to 0.1. So this is its range, total range of this diagram. Lowest is 0.08, highest is 0.1. This is dimensionless. And on right side is given relative surface roughness, epsilon upon D. And this is from 0.001, from 0.01 up to 0.05. And flow regimes are here up to from here to here to 3000. This is laminar regime from 3000 to 10,000. This is transient regime of the flow. These are Reynold number on the x-axis. Here it is written Reynold number formula with on x-axis Reynold number is rho dV divided by mu, and these are the values. These are the values, and depending on the Reynold number, you find out first relative roughness. From relative roughness to Reynold number, from Reynold number you find F. So this is practical job you should do while calculating problem, while during solution of problems. Now let's go ahead. In chilled water piping system or any piping system, just like ducts, you need volume flow controls. For that we need valves, fittings. So for valves and fittings, we use this formula. Pressure drop in a fitting is equal to, it is on two bases, either pressure drop coefficient or flow coefficient. These flow coefficients are available in design handbooks, and K is the pressure drop coefficient in this formula, and CV is the this is the flow coefficient or volume flow coefficient, CV. So if you know volume flow coefficient from the handbook, you just multiply it with under root delta P. You will get flow rate. You know flow rate and you know CV, you can find out pressure drop delta P from this formula. Similarly, delta P, if you know velocity of the fluid, you know coefficient, that is pressure drop coefficient K, you can calculate for that. Actually, these K and CVs are available from manufacturer's catalog. Whoever manufactures those valves and fittings, they give you this data of coefficients. Engineers should also know equivalent lengths of the pipes which he is using, because elbows, T is fittings. Here it is given pipe diameter 90-degree elbow, Here it is given 45-degree elbow. Here it is given T's, side branch T's and straight branch. T has two branches, straight and side branch. This is T. Look, my two fingers, this makes T. So this pipe flow is from this side. So this is straight T and straight branch, and downward it flows going this at 90 degrees. This is side branch. So depending on side branch and straight branch, you find out the pressure drop, equivalent length of the elbows and teeth. And for valves, here it is column open globe valve. There is a shoes called globe valve. These are the types of the valves. So open globe valve type. So if globe valve is open, not closed partially, then partially closed, then data will be different. But fully closed globe valve, there is a resistance, there is obstruction in the flow, and it causes this much equivalent length. As if there is a pipe this much of the length. So depending on diameter and depending on the fittings, you find out equivalent length from this table and do the calculation. This you will see in the problems. I will give you short problems also. This is the chart like you have seen in chapter 6 for ducts, but it is rather different because it is fluid. Fluid is water now. So flow rate is given here on x-axis, and vertical axis pressure drop is given partial. So given pressure drop is given Pascal per meter, pressure drop coefficient. Backward slanted lines give velocity, these 4 meters per second, 3 meters per second, 2 meters. So these are velocity lines, and forward slanted lines give diameter in millimeter of the pipe. So diameter of the pipe in millimeter can be read from here 15, 20, 25, 35 like that. So this tool, calculation tool, is used for solution of problems of chilled water design. But remember that this is for one particular type of pipe. That is called, read in the caption, pressure drop for water flowing in scheduled 40 steel pipe. So GI pipes are of two types, mostly two types used in engineering for chilled water HVAC system. So schedule 40 and schedule 80. The difference is for heavy high pressure we use schedule 80, for normal pressure we use schedule 40. So with, the difference is thickness of the wall. So inner dia may be different for these pipes. That's why you have to use pipe tables also to find out inner dia depending on which type of pipe it is. Similarly, copper pipes are of three types, K, L, M, used in HVAC systems for refrigerants, etc. So K, L, M, it also they are differentiated because of wall thickness. Depending on pressure inside, we choose thicker wall for high pressure system and thinner wall for low pressure system. Another parameter is temperature. So 20 degrees centigrade temperature. Temperature is important because in calculation comes density. In formula you have seen in Reynold number there is density. In delta P formula there is density. Colebrook formula there is density. Everywhere there is density. More density depends on temperature. So changing the temperature will change the calculation. So this table is for 20. What about if water temperature is more than 20 degrees? Then in this case, we'll go to this table, which is correction factor. If 20 degree, you will find no correction. So if higher than 20 degree, so its correction, it will be multiplied with a factor which is less than 1, like this. So it depends on velocity. Different velocities are given here, and you will use this curve depending on temperature. 40 degree temperature, for example, 40 degree temperature and velocity equal to 1 meter per second, you will use 0.95 as a correction factor of calculating pressure drop from this chart. From here, from this chart, we apply correction factor with the help of another chart. Now, let's go to next slide. And this is about, I've told you there are two types of GI pipe used in industry. That is, one is called schedule 40, other is called schedule 80. So dimension of steel pipes are given here. Inner size and outer size. This is for schedule 40 pipes, schedule 40 and schedule 80. Here is schedule 40 in this column, and this is schedule 80 in this column. You can see their inner dia is different. Schedule nominal dia is described in the catalogs or in formula. For example, 40 mm nominal dia pipe. So here 100 mm nominal dia pipe will have outer dia equal to 114. So outer dia is same, but inner dia is different for schedule 40. For schedule 40, inner dia is 102.3 mm, but for schedule 80, inner dia is 97 per minute. Why? Because thickness of schedule 80 pipe is higher than the thickness of schedule 40. Outer dia remaining same, inner dia will change because of thickness. So you find out inner dia from this table depending on schedule of the type of the schedule pipe. There is density and velocity of the water at various temperature. You need this for calculation of Reynold number, and for calculation of delta P you will Darcy formula, Darcy-Weisbach formula, and Colebrook formula. You need this density, and density depends on temperature. From there, temperature is mentioned from 0 to 100 degrees centigrade, and viscosity. You can find in this table viscosity and density both. So viscosity and density. Viscosity units are millipascals here, millipascal second, MPa second, millipascal second. So you have to multiply these with 10 raised to minus 3. These digits in your calculation. For example, at 60 degrees centigrade, viscosity of water is 0.476 multiplied by 10 raised to minus 3 Pascal second. So density is 983 kg per meter cube. Now, dimension of the copper tubes, I have told you, if in the problem copper is mentioned, then you have to select from here inner diameter, because copper may be K type and L type. K type and L type, just like GI pipes have schedule 40, schedule 80. Copper pipe has no schedule number, it is type K, type L. So type K inner dia is less, type L inner dia is more. That means type L is thinner than the type K pipes. So outer dia will be same, but inner dia will change depending on it is type K or it is type K or type L. Now, engineers, mechanical engineers, or any other engineer who is designing system to work, he has to fulfill various requirements, but these requirements are contradicting. If you fulfill one requirement, okay, that's good, it may contradict another requirement. So you have to set back from that requirement, go back and make some compromise. So that is called as design constraint. So noise, for example, noise level should be reduced, requirement is noise level should be reduced, and erosion level should be reduced. So this means velocity should be reduced. So but when you reduce velocity, then friction will be increased. So required flow rates of the water should be maintained. So what if you reduce the if you do not reduce the friction, then water flow will be cannot be maintained. So pipes and fittings should be strong enough. Again, burst or water hammer. So there are two requirements: strong enough, and again bursting and water hammer. It should be strong enough to be the internal pressure as well as water hammer. What is water hammer? This I'll explain at the end of this lecture. Water hammer. Now, depending on life of the system, aging allowance. What is aging allowance will also be mentioned. So aging allowance, when you see when pipe becomes old, right now your calculation says that half-inch pipe is enough, GI pipe, if it is hot water pipe or chilled water pipe. But with the passage of time, inside the pipe will accumulate certain deposits. So those deposits are very hard, like calcium, like stone, and just like on your teeth, you see plaque is deposited, and they're like stone, they're like calcium, and dentist stretches them. So inside the pipe, complicated system, you can't scrape, you can't insert any tool to clean them. So what we do is at the time of design, if calculation says that pipe size ½ inch is enough, we will make it ½ inch. If calculation says 1 inch is enough, we will take 1½ inch, because this pipe will work for 30 years, 50 years, maybe more. So for these 30 and 40 years, there will be deposit inside, and inner pipe size will be reduced. So even after reduction, pipe size will be equal to your calculated size, and your system will work. So this is called aging factor. So now time is over. Rest of the lecture I will continue, inshallah. The next lecture is tomorrow at 9:40. Okay, till then, Khuda Hafiz.